Hey y'all, what's up? It's your boy Linford over here, dropping a video about the different types of functions. In this video, we're talking about different types of functions and their domains. As always, if you like the content on this channel, if you like this video, if you want to get credentialed, make sure you like, subscribe, drop a comment, and ring the bell for notifications. Alright, we're starting off by talking about different types of functions. One of the main types of functions you always work with is the linear function. The linear function has two ways of thinking about the basic form. The basic form is really f of x equals x. That's the identity function, super basic, straightforward. It's got a slope of 1 and a y-intercept of 0. Okay? Very basic type. But sometimes people like to think about the basic form as just being the general mx plus b. That can work out too. Either way, just realize that the basic form of a linear equation is essentially, or of a linear function is just essentially a linear equation, okay? And if we're talking about domains, why not change up some colors here? The domain of a linear function is negative infinity to infinity. And that's always true because no matter what kind of line I draw on here, how I draw these lines, all these linear functions, they always go from negative infinity to positive infinity. Their domain, how far left and how far right do they go? They always move from negative infinity to positive infinity. So that's the domain of a linear function. Now let's chat about the quadratic. The quadratic has the basic form of f of x equals x squared. Okay, it's got to have a degree 2 exponent in there. So f of x equals x squared, that makes a quadratic, the most basic type, and it's going to look like a parabola. The graph of it's either a parabola upwards or a parabola downwards. So either of those will count. The domain of this, well, how far left does it go? Well, it keeps going off to to negative infinity, and how far right does it go? It keeps going off to positive infinity. So the domain is going to be negative infinity to infinity. And that's true for any quadratic. Whatever parabola I draw here, they're always going to keep going off forever and ever in both directions. So that's the idea with the domain of quadratic functions. Now the cubic function, the cubic one's got a very unique graph. We kind of say it has a saddle point, a particular saddle graph. Now this saddle graph, it's made up of the basic form f of x equals x cubed. This is the most basic form, or the parent function we sometimes say, of the cubic function. And the cubic function, just like it sounds, has a cubed in it, or I should say an exponent of 3, right? You're cubing stuff. And it makes this unique graph, but this graph just continues on forever and ever and ever in both directions. So when you ask yourself what the domain is, how far left does it go? Well, it goes off to negative infinity. And how far right does it go? Well, it goes off to positive infinity. So there's your domain. Now we're talking about the absolute value function. The absolute value function, basic form, is just taking the absolute value of something. That's the basic form, or as we also call it, the parent function. And the absolute value, I didn't draw it the best, but it's supposed to look like a V. It's supposed to be a straight line going off in this direction and a straight line going off in this direction, and they'll meet at a vertice there. So this is supposed to look really like a V. I'm not the best at drawing, but I think it's pretty obvious that our domain, well, it's everything from negative infinity all the way up to positive infinity. I mean, because our line just keeps going off in both directions. All right, so everything we've seen before had the pretty not that shocking domain, negative infinity to infinity, or all real numbers. We could plug in whatever we wanted into the previous functions, and they always would work. You could plug in whatever you wanted for x, you'd always get a value out for the output. However, let's take a look at the reciprocal function. This reciprocal function has something unique going on. I'll try to change up colors here, but as I move along this graph, how far left do I go? Well, I always go off to negative infinity, and then I get closer and closer and closer to 0, don't I? I keep getting closer and closer to the y-axis, but what happens is this line, let's see if I can get that a little better. Taking a look at this y-axis, I'll try to extend it a little bit. My line gets closer and closer and closer and closer to it, but I never cross the y-axis. That's the thing, I never cross the y-axis. I go from negative infinity to 0, but I'm going to put a parenthesis around 0 because I get extremely close to 0. If I keep going on forever and ever and ever, the red line will look like it's almost on top of the black line, but it won't be. It'll be so minutely close, and it'll keep getting closer and closer and closer, but this red line will never cross the y-axis. Okay, so this is the left side of my graph. What about the right side of the graph? Well, I end up going off to positive infinity, but what about as I move left? Well, the same thing happens. I keep getting closer and closer and closer to the y-axis without actually crossing it. So I'm going to say that this, and I'll put a U in the middle, is my domain. I'm going to say everything from negative infinity up until 0, union 0 to infinity is the domain. That means everything except when x is 0, everything except this y-axis is my domain. And if we look at the graph, I hope it's pretty obvious that we can see, well, yeah, I can plug any value in for x that I want. Any value for x is going to give me a coordinate point, except when x is 0, except on the y-axis. Now you might ask yourself, well, why is that the situation? Take a look at the function here. Take a look at the basic form of the reciprocal function, or sometimes we call it the rational function. F of x equals 1 over x. Well, why is it that I can't plug 0 into the domain? Well, let's see. I would get 1 over 0 and, oh, wait a minute. I end up with 1 over 0. We cannot have that. That doesn't work because I can't divide by 0. So now I'm starting to see why, okay, now I can see why I can't plug 0 in, why 0 isn't popping up on the graph here. It's because I want to avoid having an error in my work. If I plugged 0 in, I'm going to get a big error. Okay, hopefully that's making sense to you. We'll practice a little more of this, but let's take a look at another example here. Let's take a look at another example. We're going to be talking about square roots. Square roots are more commonly the phrase, or I should say more generally, the phrase is a radical function. But we have a square root function here, and the most basic form is the square root of x. And this is what we have. It's just a single line that's curved, and it starts at 0, 0. So the domain is 0, and then we go off to infinity. So that's going to be the domain for the square root function. We start at 0 and we go off to infinity. So this is the second time we see a function that has what's called a restricted domain. Everything before was all real numbers. You could plug in whatever you wanted. But here I'm restricted to only positive numbers and 0. I can only plug in stuff from 0 and above. Well, why is that the case? Well, take a look back at this basic form of the function. What I'm going to do is I'm going to pick a number. I'm going to pick a number that's not in this domain. I'm going to pick -1. Now there's no point, there's no coordinate point here, so I know -1's not in the domain, but why is the question? Well, if I took f of -1 and I plugged it in, oh, wait a minute. Can I take the square root of a negative number in the real number system? No, we can't do that in the real number system. We can do it in the complex number system, but not in the real number system. So that's why this would give me an error. So my domain is whatever keeps this inside part. That inside part is called the radicand. My domain is whatever keeps that inside part not being 0 or not being negative. It could be 0. I can take the square root of 0. It can be the square root of any positive number, like a decimal, or even something like square root of 2. It can, all of these work. They'll give me numbers. The only thing it cannot be is I cannot take the square root of a negative. Okay. Hoping this is making a bit of sense to you, kind of the reasoning. I know we're kind of moving through it quickly, but the big idea here that we need to kind of hit home is we can now, by knowing what the domain of the general form of a function is, we can now just look at a function, look at the way it's written, and determine its domain. We do not have to start graphing these and start zooming in and looking at different parts of the graph. We can just look at it and figure out what it's going to be. For example, number 1, this is a cubic function. This is cubic, and I can tell because it has an x cubed in there. And its domain is, well, negative infinity to infinity. That's what we said before. If I have the cubic function, its domain is always negative infinity to infinity. And a quick way of asking or checking is to ask yourself, does any x give an error? Meaning, is there anything I can't plug in for x? Well, no, I can plug in whatever we want for x here. So we're good. So yeah, the domain is negative infinity to infinity. Looking at this one, I see that it's got an x squared to it. This is going to be a quadratic. It's going to be a quadratic because it has the highest exponent of a 2. And I know for a fact that quadratics have negative infinity to infinity. We just said that a minute ago. Okay, so that's their domain. I'm going to skip 3. I'm going to jump down to 4 really quick. Pretty obvious that this is an absolute value function. And I'm going to say its domain is negative infinity to infinity, because we said that's the domain of all of these, negative infinity to infinity. And number 5, that's just a plain old linear function, and its domain is negative infinity to infinity again. So these are really easy. I can just rapidly look at the function, say, is it cubic, is it quadratic, is it absolute value, is it linear, and then I would know automatically that their domains are negative infinity to infinity. You can plug whatever you want in for x. The ranges will be different, but we're not really looking at the ranges right now. I'm not too worried about the range. I'm mostly just looking at what are the domains of this. Okay, now we have the weird ones. We have the square root of 4 minus x, and we have 1 over x plus 3. Let's start with 4 minus x. H of x equals the square root of 4 minus x. Now, we said before that this is going to have a restricted domain. There are some things that we cannot plug in for x. Well, what can we not plug in for x? Take a minute, pause the video, and see if you can think for yourself, what values could we not plug in for x? What do I not want to happen with this square root here? What do we want to avoid? Okay. Hopefully you had some time to think about it. But the idea here is that we want to avoid having this be negative. So we're going to say that this, and this is called the radicand, little vocab word for you. That's the inside part of a square root. That's the radicand. So we're going to say that we don't want this to be negative. This inside part cannot be negative because we can't take the square root of negative numbers in the real number system. We're only working with real numbers here. So we're going to say that this inside part, 4 minus x, has to be greater than or equal to 0. It could be 0, it could be anything greater than 0, but as soon as it's less than 0, it's negative and it doesn't work. Okay, so let's go ahead and solve for x. Let's subtract 4 from both sides. Negative x is greater than or equal to negative 4. Divide both sides by negative 1. I get an x, I get a 4. Remember, this is a little side note from when you work with inequalities. Anytime you multiply or divide by a negative, you have to flip the sign. That's a good note to have down. Anytime you multiply or divide by a negative, you have to flip the sign. So this says x is all the numbers less than or equal to 4. So that means our domain, the domain for this is everything from negative infinity up to 4, and including 4. That's what it means to be less than or equal to 4. Everything from negative infinity all the way up until 4. So let's think about this for a second. I sometimes think it's helpful to test this out. Let's pick something in this interval. What's a number less than 4? Let's try 0. So let's try the square root of 4 minus 0. Well, that's just the square root of 4, which is just 2. Okay, that's not too bad. What about a negative number? Because this says I can plug in negative numbers for x. Let's take the square root of 4 minus negative 4. Oh, what do you know? That just reverts back to being positive. So I'm taking the square root of 8. So a big thing that students tend to mess up on that you want to be careful about. I'm not saying that x is not negative. X can be negative. X can be a negative number. What I'm saying is that this whole entire inside part, that the inside part, that radicand, that whole thing on the inside, cannot be negative. Maybe x can be negative. I don't care. That's fine. What I'm saying is whatever that whole entire inside part is cannot be negative. That's what we want to avoid. All right, now let's take a look. We already got the domain of this as being, negative infinity to 4, including 4. Now let's take a look at 1 over x plus 3. I think it was p of x equals 1 over x plus 3. Now before we said that we have an error when the denominator is 0. So we need to say that this denominator don't be 0. That's what we need to avoid. The only time that I would get an issue with a fraction, I can make a fraction out of any numbers I want. I can put whatever I want in the numerator and whatever I want in the denominator. The only thing, the single number I am not allowed to pick, is I'm not allowed to have 0 in the denominator. That's the only thing I'm not allowed to pick. So we're going to say x plus 3 cannot be 0. We cannot have x plus 3 be equal to 0. So let's think to ourselves, well, what does that mean x cannot be? So let's solve for x, and we're going to say x cannot be negative 3. That's it. That's all we have to do. That's the only number that we cannot plug in. Because if I plug in negative 3, watch what happens. 1 over negative 3 plus 3. That's 1 over 0. That's an issue. That's a problem. Because we cannot divide by 0. So this is the only number that's not in our domain. I can take any number less than negative 3. I can take any number greater than negative 3. The only one I have to miss is negative 3. That's the only thing I cannot plug in. So you'll notice that reciprocal functions have this unique way of writing them. We have to write a union. We have two disjointed sets. I have everything to the left of the number and everything to the right of the number. Every reciprocal function, or I should say more generally rational function, will have this form to the domain. This is how you're going to write it, because they're going to be two disjointed sets. So the domain of this is negative infinity to negative 3, union negative 3 to infinity. Okay, hopefully this is starting to make sense to you. The big idea with this section is, hey, now as opposed to having to go and actually look at the graph, test a bunch of points and waste time, we can look at these very rapidly and determine what the domain is. Anytime you have something that's cubic, quadratic, absolute value, linear, constant, whatever, anytime that you have these, you know for a fact that the domain is negative infinity to infinity. You can plug in whatever you want. It's when you have the square roots. When you have the square roots or the reciprocals, that's when you have to start being very careful about what your domain is going to be. You have two techniques for this. Hopefully it's making sense. and you can give it a try, okay? That's it for me for this time. Again, you like this content, make sure you like, subscribe, drop a comment, ring the bell. I'm taking down Khan Academy one video at a time, okay? Hashtag Wrath of Khan, hashtag Linford for life. All right, take care. I'll see y'all later.